And these are some tips to help you graph those angles, to sketch these angles because they're a little weird. How much bigger or smaller is it than 2 pi or 360? 2 pi with the same denominator. Okay, compare to your quadrantal angles to help. So the first thing I'm going to do on this one is rewrite it with denominator. So it means I'm multiplying by 8. And then I'm going to add that's going to give me pi over 8. Okay, pi over 8 is going to terminate in quadrant 1 because it's little. But I got to go all the way around. Oops, that's a lie. Oh, no, that's right. We end up right there. This is not quite double that denominator. Negative 651, I'm going to add 360 until I get an angle that's between 0 and 360. That way I can figure out it's negative 291 where it would terminate. So we're going to add again. All right, so again, I'm comparing to 90. 90 degrees is here. 0 is down here, which means I'm terminating in quadrant 1. All right, so this goes all the way around. Nope, don't move. All the way around and a little bit more. All right, so moving on to reference angles. A reference angle, let me change this to is the smallest positive acute, so less than 90 degrees, angle located between the x-axis and the terminal. And what it's used for primarily is evaluating trig functions. So in quadrant 1, the angle itself is your reference angle. So I don't need to do anything. Prime is reference. In quadrant 2, however, here's my angle. This piece right here. The reference angle is here. So this is my reference angle. Okay, it's that acute angle in between terminal side, x-axis. All right, so mathematically, radians, it's pi minus your angle, degrees 180 minus your angle. In quadrant 3, here's your actual angle. So all of this is your actual angle. Your reference angle is between the x-axis and the terminal side. It is always x-axis and the terminal side. So kind of what they're showing you on this one is that this angle is congruent to this one because they're vertical. So this measure equals that measure. Okay, mathematically, this time it's your angle minus pi. This is on the other side. It's greater than pi. So these are, nope, use my actual pen. Less than pi or 180. And in quadrant 3, they are greater than pi or 180. And then if your angle terminates in quadrant 4, all right, here's my initial side. Here's my terminal. So it's all the way the heck around. But your actual reference angle is between the x-axis and okay, moving x-axis and the terminal side. So it's all of this in here. All right, these are just shy of 360 and 2 pi. So you would subtract from 2 pi or 360. All right, consider the angle 27 pi over 5 radians. I need the coterminal angle. I'm going to figure out where it terminates and then find its reference. So to figure out the coterminal, I need to figure out how it relates to 2 pi. All right, well, that denominator is 5, so I'm going to multiply by 5, which makes 10 pi over 5. All right, so I'm going to subtract. I've got 27 pi over 5 minus 10 pi over 5. 10 pi over 5. Well, I need it to be between 0 and 2 pi. 2 pi with common denominator 5 is 10 pi over 5. This is still too big, so I got to do it again. All right, so now we're at 7 pi over 5. Okay? Is that between 0 and 2 pi? Yeah, because 7 pi is less than 10 pi. Well, here's our coterminal angle. All right, so I'm going to figure out its quadrant. All right, so it's 7 pi over 5, so 10 pi over 5 is here. We got 5 pi over 5 here. All right, if I'm trying to figure out where 7 pi over 5 is, I can see that 7 is bigger than 5, so I know it's somewhere down here. I just have to figure out where. So we need this half angle down here. All right, well, halfway between 5 and 10. Well, 7.5 is too big, which must mean fall somewhere in quadrant 3. Okay, well, quadrant 3, if I want to find its reference angle, that reference is your angle minus pi. So it's going to be 7 pi over 5 minus pi. Get your common denominator, so it's going to be over 5. So it's going to be that 5 pi over 5. Which is 2 pi over 5. All right, now consider the angle negative 571 degrees. All right, well, obviously definitely going the wrong direction. I also need to keep adding 360. So I'm going to take negative 571, 360. Okay, that's negative 211. Okay, still too small. So I am going to add 360 one more time. So that's 149 degrees. All right, so now I'm going to figure out its quadrant. All right, I know 90 degrees is there. I know. And 149 degrees falls somewhere in the middle. All right, so its reference angle is here. All right, so I'm going to do, since it's in quadrant 2, this is 180 minus your angle. So it's going to be 180 degrees minus 149 degrees, which is 31 degrees. And I want you to notice that when I found the reference angle, I used the coterminal angle that was between 0 and 2 pi, or between 0 and 360. All right. Earlier in this section, we talked about this thing called arc length, and we talked about this formula. Okay, the formula is arc length, which is S, equals radius, so R, times theta, which is your angle measure, in radians. And I want you to underline that. All All right, it's literally like you're taking a tape measure and measuring this piece right here. All right, so find the arc length of circle, along a circle of a radius of 10 units subtended by an angle of 215 degrees. All right, so I need radius, and I need theta in radians. I already wrote it, I didn't mean to. The radius is 10. My angle is 215 degrees. I need it in radians. So I'm going to take my theta, and 215 degrees times pi over 180. All right, so that cancels. And then I'm probably just going to put that in the calculator. So 215 over 180. Oops. Then math 1. So 43 over 36. Yep, I just lost my train of thought. All right, so my arc length equals the radius, 10, times theta in radians. All right, so I'm going to take that 43 over 36, and I multiply it by 10, change to its fraction, math 1, 215 over 18. Which I would 100% change to its decimal. So I'm going to do 215, put that in parentheses like I just did, divided by 18. So 37.525. All right, assume the orbit of Mercury around the sun is a perfect circle. Mercury is 36 million miles away from the sun. In one Earth day, Mercury completes 0.0114. So it's a fraction, it's just a really bad fraction of its total revolution. How many miles does it travel in one day? So I am finding an arc length, but it's telling me the fraction of its orbit. So I can find the orbit if I know the radius. All right, now, again, let's look at this. We have the sun, and we have Mercury is way the heck out here. So I know its distance. What did it say? It's 36 million miles. Give me that. Well, I can find its orbit by finding circumference. Circumference equals 2 pi times the radius. So 2 pi times 36 million, which is 72 pi million. Since it gave me that fraction of the circumference, that's its arc length. So arc length, equals the fraction of its circumference. All right, obviously that's going to go in your calculator. So I'm going to do 0.0114 times 72 pi. And this is how you should enter it in. You need parentheses. 0.0114 times 72 pi. So 72 pi goes in parentheses. That's going to be 2.579 million miles. All right, use your answer from part A to determine the radian measure for Mercury's movement in one Earth day. All right, so we know that arc length equals radius times theta. I have the arc length. I have the radius. I just need theta. So I am going to solve this for theta by dividing by r. So theta equals arc length divided by radius. So arc length divided by radius. Okay, so we can cancel the millions and just do my regular calculator, 2.579 divided by 36. All right, area of a sector. This is the amount of, it's a piece of pie. I know it sounds so silly, but I mean, that's what it is. You're finding like the amount of pie you have. All right, the amount of your circle. All right, so this is how we get from, it is a fraction of the area. Here's your area. Here's your fraction. If we simplify it, we get 1/2 theta times radius squared. Where again, theta is your angle in radians. All right, in a central pivot irrigation pipe rotates around a center point. Farmer has a central pivot point with radius 400 meters. If water restrictions only allow her to water 150,000 square meters per day, what angle should she set the system to cover? So this 150,000 is the area of the sector. So it's your A. All right, so we want to think area equals 1/2 theta times radius squared. I have the area. I do not have theta, but I do have radius. So the first thing I'm going to do is multiply both sides by 2. That's going to get rid of the 1/2. So it's going to be 300,000. And I'm also going to go ahead and do the 400 squared, which is 160,000. And then we divide by the 160,000. So is those zeros, that's gone. One more. 30 and 16 is 2. So that's 15 and 8. So your theta is 15 over 8 radians. All right, so linear and angular speed. Linear speed, v, velocity, is speed along a straight path. And can be determined by the distance it moves along. Displacement. In a given time interval. All right, the resulting speed will be in the length unit used for radius and the time unit used. Okay, so velocity equals, this is displacement over time. This is change in position. Over change in time. So some common things that we think of velocity speed, like if I go 140 miles in 2 hours, I went 70 miles per hour. Okay, change in position over change in time. Angular speed, this symbol is an omega, results from circular motion and can be determined by the angle through which a point rotates in a given time interval. Resulting speed will be in radians per time unit. So omega equals theta divided by time. All right, so how we relate the two together. All right, definition with arc, the definition of angular speed with arc length. Arc length is s equals radius times theta. So we can plug in, if we take our angular momentum, solve for theta, theta equals omega times t. And we can sub that in for theta and get arc length equals radius times omega times time. Okay, and that relates to linear speed. Since velocity equals change in position over change in time, s being the change in position, oops, that should be an omega. Radius times omega times time, all over time. So radius times omega. Which, that's a lot, but you can have these formulas. Theta must be in radians for each formula. All right, a water wheel completes one rotation every 5 seconds. Find the angular speed in radians per second. Okay, so we want angular speed. Angular speed is omega equals theta divided by time. All right, so it tells you we have one rotation. So with one rotation, that means your theta is 2 pi. I went fully around the circle. My time, 5 seconds. Equals angle measure. So 2 pi radians divided by 5 seconds. So you would do 2 pi. Again, that 2 pi needs to go in parentheses. Divided by 5. So 1.257 radians per second. Old vinyl record played on a turntable rotating clockwise at a rate of 45 rotations per minute. Find the angular speed per second. All right, so omega equals theta divided by time. So our theta, it's 45 rotations. One rotation is 2 pi, so 45 rotations must be 45 times 2 pi, which is 90 pi. And I want it in per second. Well, our rotations are per minute. So my time is 60 seconds. All right, so omega equals 90 pi radians over 60 seconds. All right, 90 pi in parentheses divided by 60 seconds, 4.712. Radians per second. All right, hamster running in a wheel of radius 14 centimeters spins the wheel at 23 revolutions per minute. Give exact answers using pi for each question. What is the angular velocity in radians per second? Okay, that's omega. So I need omega equals theta divided by time. Tells me I have 23 revolutions, so 23 times 2 pi time, that's 23 revolutions per minute. I want radians per second, so that's 60 seconds. So omega equals 46 pi radians over 60 seconds. Now it wants exact. And so when you do exact, I just have to reduce the fraction. So these can both be divided by 2. So my exact angular speed is 23 pi over 30 radians per second. All right, well, linear velocity. Let's see where to go. There it is. Linear speed, linear velocity is radius times omega. Where to go? I have omega. (23 pi over 60), but now I need radius. Feel like if they give me that, radius is 14 centimeters. So velocity equals 14 centimeters times 23 pi over 60. I don't know why I'm writing it like that. Let's erase that. All right, so we work that out and we get 161 pi over 60, that's a lie, over 15 centimeters per second. Okay, bicycle has wheels 28 inches in diameter. The tachometer determines wheels are rotating at 180 RPM. Find the speed the bicycle is traveling down the road in miles per hour. Miles per hour, speed, this is linear. All right, so velocity equals radius times omega. Okay, well, I need omega. Let's see. I know radius is 14 inches. I know theta is 2 pi times 180, which is 360 pi. So omega so omega equals, I already forgot what it is, theta divided by time. So 360 pi. All right, so I'm going to keep omega as 360 pi radians per minute. So velocity equals 14 times 360 pi radians per minute. All right, so this equals inches per minute. I need miles per hour. All right, so 5,040 pi inches per minute. Okay, well, there's 60 minutes in 1 hour. Okay, there's 12 inches in 1 foot. There's 5,280 feet in 1 mile. So minute, feet, inches. So you're going to multiply all that together across the top, divided by all that together across the bottom. All right, so that is, I'm doing this as a fraction. I've got 5,040 pi times 60 times 1 over 1 times 1 times 12 times 5,280. So 14.994 miles per hour. All right, satellite rotating around Earth at 0.25 radians per hour. That's your angular speed right here. Your angular, I just lost my train of thought. Your angular velocity. So that means omega equals our angle per hour at an altitude of 242 kilometers above Earth. If the radius of the Earth is 6,378 kilometers, find the linear speed. So I need the radius of the satellite. So we have to imagine that we have Earth. Okay. We know its radius, 6,378 kilometers. And then the satellite up here, that's an additional 242. So the whole radius, all of this, I need to add that together to get the radius. So 6,620 kilometers. All right, well, remember that a linear velocity is radius times omega. So radius times omega. So it'd be 1,655 kilometers per hour. All right, and the last little bit, converting decimal degrees into degrees, minutes, seconds. All right, so 1 degree, okay, can be divided into 60 minutes. 60 minutes denoted by that little symbol, the little apostrophe here. All right, so 1 degree, 60 minutes, 1 minute, 1/60 degrees. Okay, 1 minute can be divided into 60 seconds, so that's your quotation marks. All right, so 1 minute equals 60 seconds. So 1 degree equals 3,600 seconds. So a lot of stuff there. To convert to minutes, okay, so converting minutes and seconds and all that into decimal degrees. All right, so convert minutes to degrees, you divide by 60. To convert seconds to degrees, divide by 60. And divide by 60 again. Which effectively means you're dividing by 3,600 because 60 times 60. All right, so we're gonna do, it's this, I did it in columns for whatever reason. All right, so we have our degree, 42, plus, and you're gonna take the minutes, divide by 60, take the seconds, divide by 3,600. That all goes in your calculator, 42.561 degrees. All right, so when you've got negatives, you want to subtract into that. So negative 300 minus 52/60 minus 30/3,600. So it'd be negative 300.875 degrees. All right, now going the other direction, converting decimal degrees back into degrees, minutes, seconds. So to convert degrees to minutes, you want to multiply by 60. To convert degrees to seconds, multiply by 60. Then multiply by 60 again. So just like with the other conversion, it's essentially multiplying by 3,600. There's a little bit of a trick to it. All right, so we keep the whole number just as it is. And you're gonna take the decimal, so this, you're gonna multiply by 60. So that's gonna get your minutes. All right, so 0.126 times 60. So 7.56. So then we take that whole number and it becomes your minutes. And I take the remaining decimal, the 0.56, and you multiply it by 60 again. So 33.6. And that becomes your seconds. Okay, so we're gonna do the same thing here. Keep the whole number, so 2 degrees. Take your 0.54, multiply by 60. It's gonna get your minutes. .4. So the whole number, that's your minutes. Then you take the 0.4, multiply by 60 again. So 24. And that's your seconds.